So today we start revision notes, second chapter, electrostatic potential and capacitance. Okay. So here the one shot video on electrostatic potential and capacitance. Okay. That's a revision class, or you can say that that is a one shot class. So first we discuss what is electrostatic potential. First concept we discuss is electrostatic potential. Okay. So definition that electrostatic potential, say the capital V represent the potential and small v represent the velocity. At a point is the work done by an external agent in bringing a unit positive test charge from infinity to that point without any acceleration. Like that, suppose there is a unit positive test charge, suppose a q naught, bring that infinite to a finite point. Okay, some points say that this point P, at point P. Okay, so work done means these are the need to work done from these charge from infinite to any finite point P. Okay, so that's work done, that is equal to Q naught test charge times potential V. So you get V equal to W over Q naught. Okay, that's the this capital V represent potential, and that potential is scalar quantity. Okay, keep in mind potential is a scalar quantity, and the SI unit is so that is the work done means that is a joules, and the test charge, so joule per coulomb, and there's another good name, that is joule per coulomb is called volt. Okay, so suppose 1 joule by 1 coulomb, that is equal to 1 volt. Suppose 1 coulomb test charge from infinite to finite point, so you need 1 joule work has to be done. Then the potential is 1 volt. Okay, so here the potential due to a point charge. Here we discuss only the key point. Okay, there is a revision or one shot lecture, that's why we discuss only key points or important topics. Okay, there is a summary class. So the potential due to point charge. Now there is the potential due to point charge. Potential due to point charge. Okay, so here there's a suppose a point charge, the potential. Okay, that's the V equal to 1 over 4 pi epsilon naught, that's the permittivity of free space. Okay, that is a source charge Q, and that's a R. Okay, suppose a source charge Q here, suppose a source charge Q here, and the distance is R. So potential at point P. Okay, so here the potential at point P, suppose say that is BP. Okay, that's a source charge, that's the test charge. Okay, and there's a potential, so if that is a positive charge, okay, so that means a positive charge for positive potential, negative charge for negative potential. Okay, so our potential is scalar quantity, but depending on the source charge, if there is a positive, there is a positive, if there is a negative, that's with a negative charge. Okay, a potential a point charge due to a system of charge. Suppose system consists a multiple number of charges. Okay, not one charge. The system consists, suppose system have multiple charges, more than one charges, or 2, 3, more than charges. So they obey the superposition principle. So potential obey superposition principle. So means that's just algebraically added. So if I if it is algebraically added here, so we get the total potential, that is equal to potential at point 1, potential point 2 plus potential at point 3 and so on. There is superposition principle, and these are the scalar sum, means the algebraic sum. Okay. Now, what is the relation between electric field and potential? That's a very important point. Okay. Relation between electric field and potential. Okay. So electric field is in a direction the steepest decrease of potential. So that is we say that electric field that is equal to minus decrease dV dr for one dimension actually. Okay, so that's for one dimension. So what is that? That electric field is the direction of the steepest decrease of potential. Keep in mind, okay. And in vector form, the electric field component in the specific direction is the negative of the potential gradient in that direction. Okay. And if the E is known, so potential difference can be right that if you know that what is the value of E, so you can write V final minus V initial, that is equal to minus integrate E dot dr. Okay, that's and if you know the potential difference, this also that is from the integral form. Okay, potential difference. Okay, so now another point to discuss is equipotential surface. Next page, discuss the equipotential surface. So the name suggests that the equipotential means the potential on the surface have equal potential. Okay, at any point in the surface, the potential will be the same. That's why this surface is called equipotential surface. Okay, so potential is same at every point on the surface. There is some properties one. Okay, some properties here. So properties number one. So no work is required to move a charge on an equipotential surface. So if there is a surface, this surface is equipotential surface. So if I move from charge one point to another point in same surface, so work done with a zero. So no work needed to move that charge in equipotential surface. Okay. Next point, point number two, the electric field always perpendicular to the equipotential surface. Suppose there is an equipotential surface and the electric field E always perpendicular to equipotential surface. Okay, and there's a point number 3, E perpendicular to equipotential surface. Point number 3, they are close together where electric field is stronger. Okay, so where the electric field is stronger, so the field are very close. Okay, okay, and they are very close. They are very close. Closer together where the electric field is stronger. Where the electric field is stronger. Okay. Now, next point we discuss the important point. Okay, that's the electrostatic potential energy. Electrostatic potential energy. Okay, so first point to discuss here, starting, there's a electrostatic potential, the okay, number one, and the number two we discuss here, electrostatic potential energy. Okay. So what is the electrostatic potential energy? So definition: the work done by an external agent in assembling a system of charges from infinite to their respective position. Okay, suppose we know that there is a work done. Okay, W by Q equal to potential. So here W equal to Q times potential. So work done associated with energy. Okay, so work done by an external agent, okay, in assembling a system of charge from infinite to their respective position. So respective position means they are actually the finite position. We know that the position where this belongs to. Okay, so that's the potential energy Q, that is equal to, we get a Q, that's the test charge, and U test charge, and a V is the source charge, one, that is a 4 pi epsilon naught R. Okay, and now keep in mind potential at infinite. Okay, if potential at infinite with a 0, and similarly the potential energy at infinite also with a 0. Okay, so that's why you get a final answer is that U equal to Q, there's a test charge, there's a source charge, 4 pi epsilon naught times R, that's the potential energy, and 1 by 4 pi epsilon naught, that is the constant. And what is the electrostatic potential energy from of Q, and suppose that is U, that is a test charge. These are the kind of potential at point charge, potential due to at point charge, that is a V. So U equal to QV, similar like that W equal to QV, that work done and energy is, no, that's the same actually. Okay, change in energy, that is also equal to work done, work energy theorem. Okay, now that point number 3, the important point to discuss here, that is conductor and electrostatistics. Conductor and okay, there are some important property. Okay, note down the property. So first property of point 1, the inside a conductor electrostatic field is 0. Inside a conductor, suppose you consider there is a conductor inside. Okay, so inside the electric field or electrostatic field is 0. Okay, inside a conductor electrostatic field is 0. So entire charge of a conductor resides on the outer surface. Okay, so here the charge belongs to, suppose there is a positive charge outside of that surface. Suppose there is a positive charge, means the electric field is outside. Suppose there is a negative charge here, the field is just that one end here. Okay, so that the entire charge of a conductor resides on its outer surface. Keep in mind, okay, only outer surface. Okay, and the point number 3, the electrostatic potential is constant throughout the volume of a conductor. Okay, so potential be the constant. Okay, because we know that here you see like E equal to dVdr. So suppose that E equal to 0 from the inside a conductor, so that is a 0. So and the potential with a constant. So here if E with a 0, for mathematically E equal to 0. Okay, so dVdr, that is equal to 0. So dVdr 0 when V is constant, because we know that differentiation of some constant by dx or dr, we get 0. So that's why the potential be constant. From mathematically, the potential is constant throughout the surface. So that potential is constant throughout the surface if electric field is 0. So electric field at the surface of charged conductor is a perpendicular to the surface. Suppose there is a perpendicular to the surface. So the perpendicular surface means that is E. So now apply here the Gauss's law. in surface plane sheet of conductor. So a 2D surface, we get E equal to sigma over epsilon naught, where sigma is the surface charge density, that is surface, that sigma belongs to surface charge density, that is the surface charge density by the surface by q by surface charge density is a q by area, that is sigma surface charge density. Okay. Now the point number 5, electrostatic shielding. What is the electrostatic shielding? That's very important. Okay, you get 1 marks or 2 marks question, or suppose a D8 question. What is electrostatic shielding? The field inside a cavity within a conductor. The field inside a cavity within a conductor is zero. Okay, we know that. That is the electric field inside a conductor with a zero. Here, you see that. Okay, where zero, the protect anything. Okay, inside from the external field. That's called electrostatic shielding. So, what is the electrostatic shielding? The field inside a cavity within a conductor is zero. We know that from this diagram. We see that inside a conductor electric field is zero, and these protect anything inside. Okay, anything inside from external field. From external field, because there is some huge number of external electric field here. Now that electric field only outer surface, do not change inside the conductor. That's why there is a protection. Okay, there is a protection, there is shielding. Okay, this protect anything inside from external electric field, from outer electric field. Okay, like example is a Faraday cage. Okay, this protects anything inside from external electric field. Suppose take an example, that is Faraday's cage. Now, point number 4 or point 4 concept. Number 4, dialectics and polarization. That's a very important. Dialectic and polarization. Dialectic and polarization. So what is a dialectic? Just first important point. If you suppose in a dialectic, what dialectic signifies? The dialectic means a non-conducting substance, or say that insulator, that can be polarized by an external electric field. That's a dialectic. And what is a polarization? The process including the dipole moment in a dialectic by applying an external electric field. And polarization is a vector. Okay, suppose the vector point P. So dipole moment per unit volume of dielectric. What is the effect? Polarization reduces the effective electric field inside a dielectric. Okay, where suppose a term some term called E0, an external field, and some factor K for dielectric constant K is greater than 1. So here, what is the dielectric? A non-conducting substance, conducting substance or say that called insulator that can be polarized by an external electric field. So now what is polarization? Polarization is the process of including dipole moment of including dipole moments in a dielectric by applying an external electric field. Applying external, these are the external electric field. By an external electric field. So polarization vector. So dipole moment per unit volume is of a dielectric. So effect of polarization, they reduce the effective electric field inside the dielectric. So that means I get a E equal to E naught, some factor reduced by K. This K factor, okay, suppose this K factor reduced for external electric field, where E0 is the external field and K is the dielectric constant. Now fifth point of this chapter is called capacitor and capacitance. That's very important. Capacitor and capacitance. So what is capacitor? Capacitor is a device to store electrical energy or say and charge. Capacitor is a device, okay, store electrical energy, store electrical, okay, say charge. Okay, that's the capacitor. And there's a capacitance. So what is a capacitance? So if you know the capacitor, so the capacitance is a C, okay, that is equal to Q amount of charge stored by potential V. So what is the SI unit of the capacitance? That is charge coulomb by volt. The coulomb by volt, there is another name is called farad. So 1 farad equal to 1 coulomb by 1 volt. So commonly it is a microfarad, nanofarad, picofarad, because farad is a very large unit. Okay. So capacitance of an isolated spherical conductor. So that is C equal to 4 by epsilon R. So here is some capacitance value. So the capacitance of an isolated spherical conductor. Capacitance of an isolated spherical conductor, okay, that is C equal to 4 pi epsilon naught times R. That's the capacitance, where R is the radius of capacitor plate. Okay, so in case of parallel plate capacitor, so parallel plate capacitor, parallel plate capacitor. So parallel plate capacitor means that is C equal to epsilon naught A by D. A is the, suppose this is a plate area with the A and another plate, two plate, and D is the separation between these two plates, that's the D. Clear? That's the parallel plate capacitor. A is the area of the each plate, D is the separation between. So A is the area, both area be the same, D is the separation between two plates. Now, with the capacitance of a parallel plate, a capacitor with a dielectric. Suppose there is some dielectric placed inside a capacitor. Suppose place some dielectric. Okay. So capacitance, a capacitor with a dielectric means some dielectric material placed inside between these two parallel plates, or suppose these are finally called parallel plate capacitor. So if the dielectric is a field with a space, Okay, suppose there's some space, free space, this is some dielectric space, that is C equal to some constant K, and that is C naught. C naught is the capacitance without dielectric. C naught is the capacitance without dielectric. Okay, and that is equal to C. Okay, that is equal to K epsilon naught A by D. That's the K. Okay, and C equal naught, that's the this value, epsilon naught A by D, because this capacitor, when some space, some air inside between these two plates, inside the plates, inside between these two plates actually. Okay, in these two plates. If a diode is partially inserted, so capacitance change based on the configuration, depending on the material. Okay, that's why the configuration should be changed. Now the combination of capacitor is very important. There are two types of combination: series combination and parallel combination. So number 6, that is a combination of capacitor. That's a very important concept in class 12 board exam. You get 1 marks or 2 marks question from each and every year. Okay, and in JEE or NEET exam you get there are some 1 or 2 marks question here also. So there is a series, some concept here. The main key concept in series, there are two types of combination, two types. First combination is the series combination. The charge is the same on all capacitors. So the key point is charge is the same for all capacitors. Okay, that's the series. Q charge means here the Q be the same for all capacitor. Okay, so the total voltage, suppose say that the total voltage V, that is voltage. Okay, the potential total, that is equal to V1 plus V2 plus V3, this V should be added. So the equivalent capacitance, so the equivalent capacitance, so equivalent capacitance, that is equal to 1 by C total, that is equal to 1 by C1 plus 1 by C2, 1 by C3, so on etc. The series combination. Now next is the parallel combination. There's another combination is a parallel combination. So what is a parallel combination? So there is a potential V. Suppose potential V, the important key notes here, very important point or key point here. V is the same for all across the capacitor. V is the same across all capacitor. V value is the same for all capacitor. Okay, say now say that the total charge Q total, that is here, just be added Q1, Q2, Q3, because the capacitor stored charge. Okay, so here the equivalent capacitance C total, that is equal to C1 plus C2 plus C3, so on. Just be added here. Now another important point, number 7 point, is very important, that is the energy stored in capacitor. Energy stored in capacitor. So here the work done, very important, that the energy, suppose when I say that energy, okay, keep in mind when I say that there is an energy, so energy also associated to work done and energy are related. Okay, they are like a twin brother or twin sister, they relate. Okay, relate to each other. So work done in changing a capacitor is stored as electrostatic potential energy. So work done in changing capacitor is stored as electrostatic potential energy. Okay, so what is work done related to here? That is the work done in charging a capacitor is stored as electrostatic potential energy. Electrostatic potential energy. That's the U. Okay. Suppose now that U, that is U equal to energy, that is 1 by 2 Q times V. So means half CV square. Okay. You can also say that half Q square by C. Okay. The three form of energy, that is very important for solving a numerical. Okay. Now the another important point is the energy density. If there is energy, so there is obviously energy density. So energy density. So energy density, that is U, that is also equal to energy stored per unit volume. Means energy stored per unit volume. That's the energy density. So that is U equal to 1 by 2 epsilon naught E square. So in case of vacuum, and E equal to half of uh, K epsilon naught E square. So in dielectric, there is a two form here. For in vacuum and in dielectric. Okay. So here now the summary of the summary class is okay, and you know the must know derivation for exam. So very important derivation for exam, important for board exam actually. The first derivation, electric potential at a point due to a point charge. Okay, so electric potential at a point due to a point charge. That's very important. Number two, relation between electric field and potential. The derivation, that is equal to E minus dV dr delta V delta R. Let's say the minus dV dr. Number three, capacitance series and parallel without dielectric, or series and parallel, okay, with and without dielectric. Number four, equivalent capacitance for series and parallel. There's a series combination or parallel combination. That's very important for solving numerical also. Okay. And number fifth, that is U equal to half CV square. These five derivations is very important for board exam. Okay. Now final, that's a quick formula sheet. That's a very important. Okay. Quick formula sheet. So first is a potential in point charge, that is V equal to KQ by R. Number 2, potential energy of two charge, that is U equal to K Q1 Q2 by R. Number 3, field from potential, field from potential, okay, that is E equal to minus del V del R or dV dr. Number 4, capacitance, okay, that is C equal to Q by V. Number 5th, for parallel plate capacitor, that is equal to C equal to epsilon naught A by D. And with dielectric or without, that is a without dielectric or with dielectric, that is equal to C equal to K epsilon naught A by D. Okay. Now series combination and parallel combination. Series combination, that is 1 by C total, 1 by C1, 1 by C2, so on. Parallel combination, C total, C1, C2 and so on. Energy store, number 8, energy store means U equal to half QV, that is also equal to half CV square, half Q square by C. Number 9, energy density means per unit volume, that is equal to half epsilon naught E square. Number 10, spherical conductor, capacitance of spherical conductor 4 pi epsilon naught R, and we know the K value. Okay, for K, actually the K is given in exam. Okay, that is 1 over 4 pi epsilon naught, and that is 9 into 10 to the power 9 Newton meter square Coulomb to the power minus 2. That's a summary class or one shot revision class, chapter 2. Okay, that's very important. Electrostatic potential and capacitance. If you have any doubt, please ask in comment section. I will try to give the answer. Okay, so there is a full lecture series here of a detailed concept. You can also check that full lecture series. Okay, I pinned that series in description box or also I button. Please check that. Okay, today in the class here. Okay, thank you.